Welcome, everybody. Thank you for coming. We have a fantastic show for you today. We have Mr. Joseph Rickert from Revolution Analytics, which is a wonderful company built around the R language that I know many of you are very familiar with and use. We also have a wonderful panel discussion on statistics. And this is really a hot area. There's a lot of debate about statistics, especially when applied to large data sets. And I'm really excited about the panel discussion that we're going to have. I want to ask that all of us please support our sponsors, especially Old Chicago. They provide the pizza for us. And after the event, we're going to walk 2 blocks over to 14th and Market and eat and drink at Old Chicago for 20 minutes, a half hour, an hour, whatever you want. But I strongly urge you to come. You'll meet new people, you'll make new friends, you'll expand your professional network, and we'll get to support our sponsor. I want to apologize to you about scheduling this on the same day that Jimmy Buffett is having his concert right down the street over here. So if you want, you can attend this event for a little while, and then 8 o'clock walk on over. I mean, it's a stone's throw away over at Pepsi Center, and probably buy a ticket to the concert cheap from a scalper.
This is the Jimmy Buffett.
That's right. But so thank you. All of you are serious people. We know that, since you're not at the Jimmy Buffett concert. I just learned that he's giving this concert today, which tells you I live in a tunnel. Anyway, I want to also acknowledge my right-hand man, Mr. Michael Malik. I couldn't do this without him. He's absolutely fantastic, and Michael, thank you for your wisdom, your help, and just making sure I don't do stupid things, which I'm prone to on occasion. Anyway, I'm going to turn it over to Joseph. Thank you again for coming.
Good evening, everybody. Yes. So what I'd like to do this evening is talk to you a little bit about all these parts here. My talk is, I hope to have 3 sections. First, it's going to be a reprise of the talk that I gave at the USAR conference in Spain over the summer. And then I'm going to set up and talk to you a little bit about what Revolution Analytics is doing in the Hadoop R world. And then if the gods are willing, we'll actually see some code and do a demo. So before we start out, let's, how many people here are R people? Wonderful, excellent, because you'll see that I have an R bias, and I'm not going to be apologetic about that. We all have our biases. So, first part is to talk about the 3 realms. And what do I mean by that? Well, the intro is the hype. So big data, data science, I mean, we've all been enveloped in this hype. So this is where we were 5 years ago, the end of theory. Just data was going to make any kind of statistical modeling theory totally obsolete. Then 2013, it's still, the hype is continuing. And then you get quotes like this. I'm sure you know Mr. Taylor, but never judge a man on a single tweet. I mean, it seems outrageous, but we don't know how we got there. So this is, but this is the world of the hype. And what I'd like to do is see if we can't get a little bit beyond the hype. And the way I see it, we have a collision of 2 cultures. We have a collision of data mining, machine learning, programming, computer science culture on one, which are again separate little cultures in their own right, and then statistics and statistical inference. And this is kind of my Bayesian prior word cloud on what my world looks like. So mean, these terms are crazy. I mean, I work for a company called Revolution Analytics. What kind of word is analytics? I mean, when did that really enter the mainstream? It's here to stay. Data scientist. How many people here are data scientists? All right, my title is data scientist too. Now, you have to realize that if you're a data scientist and you're introduced in a room full of physics people or biologists, how many people here are those kinds of scientists? All right, so the term data scientist to those kinds of scientists often sounds fishier than political science sounded, or social science. So that's because it's brand new and people have no idea, where it's going. So the people here, we're all helping to invent what this is going to be. So the first part, what I hope to do here is we're going to talk about the practical aspects of doing statistics on large data sets. So that's my other bias. So I'm from the statisticians camp. Before I started working at Revolution Analytics, I was working as a statistician for a small healthcare economics firm. And way back in my career, I started out building mathematical models when programming was on, punch cards and what have you. So clearly I chose the right road then. What rules, and so then we'll move to my R bias. What tools do we have to meet the challenge? And then I want to say something a little bit about maybe, where some theory would help in all this. So this is my take on the universe. This is the sweet spot for doing statistics. Now, not that you cannot do statistics in some legacy system, where you've got a package where you're working in pull-down menus, or you're working in Excel, or you're writing your own code. But this R has become the standard for doing computational statistics. And the reason why, I believe, first off, because it's a language, it's an expressive language that helps people think statistical thoughts. So those of you who program in R, you know that it's a functional language, and it objects. It has an object structure, and the objects are things that are meaningful to statisticians. So when you build a linear model or you do a regression, you get a model object that has pieces with it, that pieces of data that travel with it, that you can manipulate as a whole. So as opposed to doing things maybe in a package where you set things up right, you put the inputs in, you get outputs, and then you might get flooded with printed results. In R, you get back almost nothing unless you ask for it. And what your next step depends on what kind of a flow you in. So that's what I mean in the flow. So you're doing statistics with R. There's a sense of, oh, I didn't get that, look at this data. Yeah, I wonder what that looks like. So you graph that data. Or you say, oh, I didn't get this. Well, let me go back and do that. So there's a sense of always moving forward and you really can lose yourself. But that kind of working is in what I call the first realm. This is the realm of where all your data are in memory. So I'm a data R guy. Sometimes I say data is, but how many data R people in here? How many data is people? Yeah, we're losing. We're losing. So as beautiful as a language as R is, it was designed at a time before we had all these clusters and ability to do parallel computing. It's growing into it, as I'll hope to show you. But basically R, in its raw form, is memory bound and single threaded. So you have to have all of your data structures present in memory along with your code. The rule of thumb that I use is that if you think you want to analyze a data set in open source R without doing any kind of extended things like I'm going to talk about, then you have to have about 4 times the amount of memory than the file size you want to play with. So that's a challenge to get around that. Now the next realm is the realm of chunking. And we're going to talk about that. And that's where the data are too big to sit in a single file. You can't fit them in memory, but they fit in a file. So the strategy is going to be this chunking strategy. You have your data on the disk somewhere, you read some data, you do some intermediate computations, you save them, you read the next chunk, you go through like that, and eventually you assemble something into a final result. So that's the chunking realm. And the third realm is the realm of massive data. So maybe you've got so much data that you can't even stick it on a single server. That you have to have the data spread across multiple servers and tied together with some sort of file system like you have with HDFS and Hadoop. So I know there are other massive data structures, but Hadoop's getting all the buzz, or most of the buzz. And it's a good stand-in for everything else. So those are the 3 realms of doing statistical analysis. And when you're down here, it feels like doing statistics. So my contention is that when you're skilled with a language like R, and that it's almost like working with math. I mean, it's pretty close to it. There's a different vocabulary, different set of symbols, but you can think those kinds of thoughts. Once you're in this realm, it feels like a whole different thing. It doesn't feel like doing statistics in the same way. And the feel, I mean, you know, the way you operate and the things you can do. And I want to explain what I think is going on here. So, the realm of chunking. So first off, you have these external memory algorithms. And that's what I just described, where you have the data sitting on a disk and you have to go access a chunk and bring it in. Next, you have the opportunity, and this is the big thing, the opportunity for distributed computing and parallelism. So, you know, it occurs to you from when you're moving from the bottom up, oh, I got different chunks. Well, maybe I can do stuff in parallel with the different chunks and get things done a little faster. But you have to change your way of working. So here's what I just described as an example of kind of a schema for doing an external memory algorithm. And little things happen when you start to do this that change your way of working. So I'm dropping down into a detail here, like dealing with factors. So one of the wonderful things that R does is deal with categorical variables. So if you're a statistician, I mean, you need to be able to deal with categorical variables. So in R, we call them factors, and there's all kinds of helper functions for dealing with factors. But when you're in the chunking world, you've got, I don't know, maybe 100 million or more rows, a billion rows, something like that. Who knows when you're going to see all of the levels in the factor? I mean, you might go through quite a few lines before you can see everything. If you're writing your own code, you know, it might be difficult because it's hard to, it's just straightforward housekeeping, but to write code where you're going to keep track of different levels, and then when you come to data cleaning, you know, if you have a large data set and it's something, maybe it's customer driven, where there's a lot of latitude, even just addresses. Sometimes people abbreviate streets, sometimes they don't. Sometimes people abbreviate cities, sometimes they don't. So you could take something that has maybe something on the order of 1,000, 10,000 real levels that you want to look at. And in this kind of world with a large data set with all the permutations, you might have 100s of thousands of levels. So it's not, I don't know, maybe 100 million or more rows, a billion rows, something like that. Who knows when you're going to see all of the levels in the factor? I mean, you might go through quite a few lines before you can see all of the levels in the factor. problem that can't be overcome, but I bring it up as an example. It kind of slows you down in your flow. It's some more detail to be attended to. And here's an example of a small chunking algorithm. Maybe things are working well, I'll run it for you later. But all it's doing is tabulating. Down in the details here, we see we're writing a function called chunk table. And it's going to tell you how to process a chunk of data. So you see there's it calls our table function. And then there are two variables, RxGet and RxSet. So what it's doing is it's computing a table. It's setting it so that it'll be available in memory for the next chunk. And it calls the get function when it gets to the next chunk and just accumulates the information. So it's just a simple accumulating function. And we're calling that function from within a function called RxDataset. So I'll talk in more detail about these Rx algorithms later, but basically they're what we call PEMAs, parallelized external memory algorithms. So if you're a salesperson, you always say parallelized external memory algorithms, and no wonder why people don't buy them. But so parallelized, not paralyzed, external memory algorithms. And here we are in distributed computing. Now, as I said, when you're starting from the bottom up and you realize you have these chunks and you can work in parallel, well, then there's an upside, right? But what breaks the flow again is now you have to deal with cluster management, data storage, data allocation strategies. Now herein, this is what separates the boys from the men and the women from the girls, is if you're going to be a data scientist, you got to do all this yourself. So an older paradigm of people doing statistics, you'd have the PhD statisticians thinking about theory, and then there'd be a whole layer of people who would actually write code. And it still works this way in the biosciences. Anybody here work for a gene company or a biotech company? It persists. I mean, there's still a lot of people using SAS in that kind of environment, and they have that kind of structure. But if you're going to be a data scientist, and one of the things that I think about as being a data scientist is that you have to have the ability not only to think about the statistical inference, but you have to be able to fetch your data and write enough code to apply the algorithms you're interested in, and before that, to clean the data and get it in shape. So again, when you're moving in this area, yes, it's wonderful to have opportunities for statistical computing, but it can be painful. So you're changing your way of working. And so let's look at some of these things. Everybody learned in school that you evaluate whether or not a regression model might be any good by examining residuals. Well, you can't do that really if you have hundreds of millions of rows. There's not even much of this kind of statistical practice and lore about how to give a educated gut check on whether or not your regression model was working had to do with visually looking at diagrams. You compute Cook's distance and various things. You look for leverage, you're looking at stuff. You can't do that. Now, in fact, you get to the point where if you're not going to look at the residuals, maybe you don't even want to compute them. So you have to change your way of working, and this is a change both on a practical level of how you're going to work, you're going to build the diagram, and a theoretical level, how you're going to tell whether you've got a good model or not. So there's a lot of unanswered questions I maintain there, and statisticians and people who use statistics are struggling with this. Plotting what you see may be difficult. There may be a limited number of functions for you, because if you're writing your own external memory algorithms, obviously there's only so many you can do, and even if you're using a very robust system like Revolution Analytics package of RevoScaleR, it's an R package that implements these parallel external memory algorithms. Even there, we have limitations. There are only so many functions that we've managed to complete so far. So you're likely, maybe you have to do some real programming. And another point that I want to mention here, and we'll talk a little bit more later, there are different kinds of algorithms that are developing. For example, one of the things you don't want to do, even when you get to a small data set, 100 million rows, small data set these days, you don't want to sort the data if you don't have to. You certainly don't want to sort if you're working on Hadoop, but you don't want to sort even at that level. It just takes too long. So if you don't sort, how do you compute a median? So I have a good friend who works at PayPal, and he was working with R and data streaming on the eBay production cluster. And he told me that he started a job, he writes some R code, and he had this standard summary function, summary of some variable. So in R that gives you the min, the max, the mean, the quantiles. And he got a call, he forgot about it. And 2 days later, he got a call from the production operators asking what he was trying to do. His job was going to bring the system down. So he was sorting on the eBay production cluster. So you don't want to do that, but there are ways around it. And the ways around it are there's some well-established algorithms on how to estimate quantiles. So you start moving yourself into that realm of different kinds of algorithms. Now, so dealing with these are just, they're not random, but these are some ideas for dealing with in the chunking realm, dealing with data that's too big to fit in memory. So in the open source R world, there's a R package called Big Memory, which is well-established, written by a couple of Yale statisticians. Anybody use Big Memory? All right, how about FFbase? It's another package. So these are basically R packages that enable you to work in the chunking realm. You can work with chunks of data at a time. You don't have to have everything resident in memory. Then there are some, so one of the ways I like about, so R never is static. And one of the really good hallmarks of a tool that is going places is when people push at the edges and the boundaries and try to make connections between R and lots of other systems. So there's a package called SciDBR, which gives you great access to the SciDB database. And this is a special database for manipulating large matrices and arrays, multi-dimensional arrays. So it's kind of specialized. It's the kind of thing you might use if you're an astronomer or had incredibly large matrix data structures. And there's a way to get at it from R. And you can, yes?
So does that need to be a sparse matrix?
No.
Oh. Okay.
Doesn't need to be, but could be. It deals with sparse matrices. And then there's for parallel computing. So there's the RevoScaleR package, which I'm going to talk about in detail later. That's what Revolution, that's how we make our money. So Revolution Analytics, we're the cheerleading company for the R language, right? We do our best to support the open source R community. We contribute occasionally packages back into open source. So most of the early packages that deal with parallel computing in R were written by people from Revolution Computing, and that's before we changed our name to Revolution Analytics. And so we provide our own distribution of the R language to businesses and industry. So here's just a 2-minute commercial. So what we do is we take open source R and we recompile it. We surround it with services and support, and we have some proprietary code. Most of that is this RevoScaleR package that I'll be talking about for dealing with large data sets. And basically what we're trying to do is to help those corporations who just can't do free. You know, find many a company where open source is difficult, and we're here to help those people. And the algorithm that I'm going to talk about, RxD tree, is another in a new class of algorithms, like the algorithm that I talked about for estimating quantiles. And of course, how do you visualize? Anybody a ggplot2 user? Good. So you know in ggplot2, there's some provisions there with you can scale down the intensity thing, and that helps to help you plot lots of data points. But still, if you have gazillions, what are you going to do? Well, Hadley's working on Hadley Wicken, a ggplot2 author. He has a new package called InViz, and then there's some other people working in that area with new techniques for plotting very large data sets. So that shows you the robustness and the drive of the community working around open source language. So here is an example of an algorithm that's in this new class of algorithms that is motivated by working with very large data sets. So this is anything that begins with an Rx in front of it is an algorithm from that RevoScaleR package I talked about. So this is a tree algorithm. Think RPart. People here use RPart in R, decision trees or classification or regression trees. Yeah, so that's what we're talking about here. But what we did that makes it a little bit more interesting from the big data point of view is that based on this algorithm that those two fellows came up with and published in 2010, we don't build the trees on the data themselves. We build the trees on histograms. So you can think of a histogram as a summary of the data. And it's a stand-in for the empirical probability distribution. That's the kind of thing I see happening now, is that people building classes of algorithms that are like one step removed from the raw data, because if you're going to work with billions of rows, trillions of rows, lots of variables, so you have to make this adjustment. It's a new way of thinking. And these algorithms are not... They work really well in the sense that if you set the parameters in a certain way, you can get exactly the same results as if you were using, say, RPart or a classic decision tree. It works on the data themselves. But obviously, you want to get beyond them. You want to move to a space where you're using these histograms instead of the data themselves. So you have to understand, how do you characterize that algorithm? Well, there's some theoretical results published in that paper, and I really encourage you to look at it. For instance, that if you, if you make the number of histograms large enough, you're going to get the same results as you would if you worked on the data. Or if you build a tree with this kind of algorithm and you use enough data points, what's going to happen is it's going to converge to a model that will have the same error characteristics as the original, as a model that's built on the data themselves. So now, this is a way of changing your way of thinking if you're really careful and you're interested in doing statistics. If you're a brain-dead data miner, you don't care. You just want a tree classifier, press the button, it gives you a classification. End of deal. But if you're a statistician and you're interested in inference and understanding uncertainty, you have to understand what these algorithms are doing. And I think that's hard, and it kind of breaks your flow a little bit. You have to think harder and harder. So it's a new kind of world. Now we come to the world of massive data. And so now, the big deal here, from the point of view, I think, of having, I got beyond the boundaries, the big deal is that the cluster is given. That doesn't, so now parallelism is not kind of an upsign. Parallelism is, oh, I have to do everything from the beginning in a parallel way. So it's not a matter of writing some code mostly and then checking it out for most people and then writing your MapReduce job. You know, you have to write different code. So it's an area of interest that I'll show you that Revolution Analytics is involved in. But for most people, when they want to make this jump to working in the Hadoop world, you got to learn to write MapReduce jobs. And it's doable, but difficult, and it really slows down your flow. And then some basic tasks become, you know, very difficult, like random sampling. Okay, random sampling in a Hadoop world is not just a slam dunk if you really want to have it random. So, first off, any kind of MapReduce job where you want to produce, like, say, exactly some number of samples, like exactly 10,000, is a little bit difficult because when you're writing MapReduce code, you really don't want to have too much communication between all the mappers and the reducers. So if you're going to get exact number of rows, you got to have some communication. The other thing is, if you want random samples, you want to have a really good random number generator. There are plenty of them available for R. Even Excel has a decent one now after they fixed it a number of years ago. But when you're in this kind of world, the data points are so big that you might overlap. So now you have to have parallel random number generators. So there's a whole class of random number generators that assure independent streams that they'll pass all of the tests for randomness, even though they're being generated independently. So it's one more thing for you to know about. And if you're careful and you're a statistician and you want to make a careful inference, again, it's more hard thinking, more people developing, incredibly smart people developing these tools, but you have to think when you're using them, and it, you know, breaks the flow. So that just is what I said before. So you've got some serious programming, and for most people, it means multiple languages involved. So once you, you know, we Revolution Analytics, we're trying to make a case that you never have to leave the R environment. So that's our game. But you know, we're not totally there yet, and I'm sure there's many practicing data scientists have at their fingertips a number of languages. So, you know, everybody uses what they know, but some people might want to use Pig if they're in the Hadoop environment, or they're Python people. So when you get to this world of big data, your massive data, then you're often in the world where you have to use multiple languages. And R, again, one of the strengths of it is this ability to integrate with other systems, is that R has quite a nice number of interfaces with different systems, one of them being C++. So the R language itself, much of it is written in R, but underneath it is C code and C++ code. So if you want to do things in R and you find out that you've got some performance impediment, well, you can call C++ code relatively easily using the R CPP library. So again, numbers of smart people like extending the boundaries and pushing the environment for R. And this is what I just mentioned, the difficulties in working with random samples and working through parallel. So these kinds of things, I wouldn't say that they're certainly not deal killers, and they're not deal killers for anybody who works in this area. But if you're going to be careful, you have to develop those skills and take the time. Now here's a quote that I'm sure will come up in the panel discussion. Because this is what I think, as I started out, I talked about a clash of cultures. There's some people that believe this religiously. And I think as carefully as it is, it's fairly carefully worded, and I believe it is true for the environment and the class of problems for which, the Facebook and the Google people are working. But other people look at this and they immediately jump to the conclusion of use all of the data all of the time and forget with statistical models. And there's where you fall, I believe, off the cliff into the dark side of ignorance. So one of the things that I think the theoretical statisticians could do would be to be more helpful in illuminating the class of problems for which this makes sense, and for describing what they think of as big data in a reasonably intelligent way that is accessible. So we can talk about that later. I have some ideas there, maybe during the panel discussion. So here is the way that if you want to work on Hadoop from the R environment, what you can do now. There's a open source project called RHadoop, and we're one of the people behind that. We're the primary funders of that, I guess. But it's an open source project. And what you're doing is, you're having, this is a schema of a Hadoop platform, and you have R running everywhere on the platform. And there are 3 basic packages that are in this RHadoop thing. And the main one is RMR. And what enables you to do is write MapReduce jobs using the R language. So, you don't have to write it in Pig or some other type of language. You can stay in R and write R MapReduce jobs. Is there anybody here who uses this or who has played with it? Excellent. So, maybe we can talk about what you think about it later. So here, this ends basically the first part of my talk. And what I'd like to leave you with are some references that I think are really helpful in sorting your way through the clash of cultures between the machine learning community and the statisticians and statistical inference community. So the first thing is a paper by Leo Bremen, the guy who invented trees and random forests and what have you. He had a tremendously smart guy, and he wrote a very prescient paper there talking about the clash of cultures. And of course, this 2 cultures idea is a reference to C.P. Snow. Everybody knows C.P. Snow. Good. C.P. Snow was a very a polymath kind of person who wrote, I guess, mostly in the 40s and 50s, and he was talking about the 2 cultures basically between the humanities and the sciences, especially at a time when people were struggling to integrate things like quantum mechanics. So, for mathematical formulations of some of these big issues, I picked out these papers. These papers by Donahoe are pretty difficult, pretty going, but I think they're the real deal. The machine learning papers, the quote I got was from Lin and Raboy. So that's an excellent paper and really worth looking at in detail if you're interested in the data mining and inference. And we have statistical techniques for big data. And then here are some papers that are the background for that RxD tree algorithm that I spoke to you about. So I'll put them up there again. It probably will make the slides accessible. So, bridging the gaps. So, by the gaps I mean moving from one realm to the other. So moving from the in-memory realm to the chunking realm, moving from the chunking realm to the massive data realm. And this is just a schema of RevoScaleR. So what we have, it's a package, as I mentioned. It's exclusively available as part of what we call RevolutionR Enterprise. That's Revolution's distribution of the R language. And it implements these schemas, and it provides functions to do what needs to be done. You need to acquire data imported from various sources. You need to clean it and manipulate it. And then we have algorithms for actually doing statistics. And it scales quite well. So I hope to show you some of the ways that it scales. So these are some of the functions that you have available from the statistics point of view and cleaning. So here we call it the data stat, and we actually named the function that I showed you before, RxDataStat, kind of in respect for SAS and the stats data step and its ability to manipulate functions. So they've always done a good job there, and it's a problem area. If you want to work with big data, you have to have good data stat, data manipulating functions. So we have those things. We have some descriptive statistics. And now I'll get to the schemas. So what are these guys? So they're written to implement chunking in an efficient way. Again, that's another schema. So what you have to do is you initialize something and you process a chunk and aggregate and finalize. So here are a number of algorithms that we have. So we can deal with large correlation matrices. That's if you have the ability to compute the correlation matrix, you can often take the results of using a RevoScaleR function and then manipulate it with some standard code and do something. Maybe you do PCA or something like that. You have to, if you can get to the correlation matrix. So one of the things that I'll show you, the demo goes well, is that we've written these Rx functions, so you intermix them with standard R functions. So you do a logistic regression, say, on, and you get a model object, and then you use a standard summary function from R to provide a summary of the model object. So that's the way you want to work. That's the obvious way to keep the flow going. And in particular, these functions, they scale. So they scale well in multiple dimensions. So they scale really well. So statisticians all think of rows and columns, okay? So the rows are a number of different observations, and the columns are your explanatory variables. So these things scale linearly with the number of rows. So you can work with very large data sets from the number of rows. They scale fairly well with the number of columns. But when you add columns, you're just not adding more work for the algorithm to do. You've got all kinds of statistical, traps that you can fall into. So if you're dealing with 40 variables, well, maybe you're not going to have, multicollinearity. With 4,000 variables, yeah, maybe you've got all kinds of trouble, and especially if you really don't know the province of your data set. And people who are trying to do things with thousands of explanatory variables, they're usually coming from the machine learning thing where they don't really know. They just, I'll put it in and see what happens, right? So you can't expect it to scale linearly in that domain, but it scales pretty well. So we've built some relatively big models there. And there's different ways that, you know, you can see scaling. And then it scales well with in different kinds of environments. So whether you're just working on a PC or you're working on a cluster. Here is a chart that we do to show. So what we got here is we're doing a GLM, so the generalized linear models. These are like the crown jewels, I think, of the RevoScaleR package. And you see, this is the GLM, and the blue line is trying to run the GLM, the open source GLM function. And it's basically running, down the bottom here, you have the number of observations in your data frame. So on whatever, this is probably a small machine, but the principle is the same. You get to a point where R spends too much time. If you're trying to do everything in memory, it just becomes paralyzed. You can't deal with everything. Whereas you can see the RevoScaleR function is moving along, and it's doing quite well. So, why are they so fast? Yes?
On the previous slide, was your architecture at HDFS?
No, that was just a laptop.
Just regular R?
Yeah, just open, I'm just showing there regular R on a laptop running out of steam.
Gotcha.
And people want to know, well, what's magic about these algorithms? Well, there's nothing magic about them. They're just built with a lot of attention to detail. So that's what we've been doing for a number of years now, is building these algorithms, paying attention to using C++ underneath, threading, the distributed computing architecture. And this is basically what our architecture looks like. So our idea is to be able to run R on a laptop and take the same code with hardly any changes, and then run it on a server, and then run it on a cluster, and now with the new release, to be able to even run it on Hadoop. So the idea, what we've done, so here's the package of these schemas. And then what happens is that it sits on on layers of software, kind of like a protocol stack, that have to do with efficient communication. And on the right, over here, you see that we have the ability to run this code on different clusters. This, the top two, it's not shipping yet. The top two is in the new version of the software, which will be available for GA at the end of the year. But you see, we started out for a number of years now. We've been able to run on Microsoft HPC clusters and on Linux LFS clusters. And now we're moving up, and then we can run in database in Netezza and IBM Netezza. So the idea is to move up the chain of platforms that are dealing with massive data, and to do this by just changing what we call the compute context. So you have some code, you set your compute context for one thing, you want to run on your laptop to develop an algorithm. You work there with some small data set that you have on your laptop. Then you want to go run a production thing that's on a cluster somewhere. You take the same code, but you change the compute context. And that sets up for this new thing I've just mentioned on running R and Hadoop. So this is the goal. And we want to be able to have you run our code our R code, to run our code without actually having to write the MapReduce jobs yourself. So for a few things, we've achieved that, and I'll be able to show you. And here's kind of how it works. So this is a schematic of a kind of Hadoop cluster. So here's me, say, on my workstation, and here's an edge node, and here's the job tracker. And then you have the worker nodes, and then you always have a name node up there. So you start out, and then you send it to the edge node and the job tracker. The name node get involved, then all the worker nodes get involved. Now, if you're going to run the RevoScaleR algorithms on this cluster, you have to have R on all these nodes. And so you start out, here's your job, and it's moving towards the edge node, and then it'll get distributed towards the worker nodes. So the way things, this is all new, and I'm just learning about how this works myself, but basically when you have a R script, it's got all kinds of functions in it, some open source functions intermixed with these schemas, the RevoScaleR Rx functions. The Rx functions are the ones that get distributed across the cluster. If you're just executing something, an in-memory function, an ordinary open source R function, then it's executing only on the edge node machine here. So you get a result, and it propagates out there, and then it comes back. So just a little animation of things moving through the network. So basically, each pass through an Rx function is a MapReduce job. So if you're running an algorithm like logistic regression, so that's done. The technique is iterative related least squares. So what it's going to do is make several iterations of the algorithm. So it is going to have to kick off a MapReduce job for every iteration of that algorithm. So there are different MapReduce jobs. Likewise, you have a logistic regression. You have some other thing, like you're just maybe doing a tabulation with RevoScaleR functions. That's another MapReduce job. So what it does is all those intermediate structures in there that I spoke about take care of interfacing with the job tracker and the job nodes and the Hadoop and what have you, getting to the data that's been distributed on the file system, and saving you from having to write those MapReduce jobs yourself. So now things work well. Let's run some code. So any questions there before I start out? I think I wanted to set the big picture on where I think we are with statistics and data science, and then this is the approach that we've taken at Revolution Analytics. It's unavoidable that if you're going to work with big data sets, you develop some set of tools, and we're for pushing our tools. Not our tools, our tools. Oh my. So, so this is what the IDE for Windows Revolutionary Enterprise looks like. If you're some of you may be familiar with this, but most of you probably use something like RStudio, and that's fine. Looks familiar to this. Just a quick tour. What we have here is this is the script editor, so I'll be running programs from here. This is the console. So R is an interpreted language, so you know, at the lowest level, it's a glorified calculator. Things execute immediately there. This shows you my global environment. And that's, that just keeps track of things I have in the file system. So what I want to do is, let me see, go here. Computer. So I'm going to run the airlines example. Some of you may have seen this, but it's a good place to set things. So I'm going to work with this file, Big Air 3. And you can see it's taken up a lot of space on my disk. Yes?
Sorry, before the screen you're showing, did I catch it right? That's your guys' GUI that kind of,
Our IDE, yeah.
okay, that has R with additional packages of yours.
Right.
And you can run it there.
Right, so, but that's not the important thing. If you buy the Revolution distribution, if you license the Revolution distribution of software, you can run any other kind of IDE you want to. Awesome. So I have this big data file. So this data file was the one used in the 2009 American Statistical Association Challenge, and it contains all of the domestic flight information, U.S. domestic flight information from 1987 to, I think, 2009. And it's got 123 million rows, and it's got, I guess, 29 variables or so in here. And let's, let me find the script I want to show you. So here's just some R code to point to the data file, and I'm going to run this rx get info command here. And what we do is we store data for efficiency in our own binary file format. So sometimes I'll be working here with data in that file format. But we can also read data directly from CSV files and import it from SAS files. So what do we have here? So you can see it's a pretty big file. So here it is. It's 123 million rows, and it's got 31 variables because I made some variables of my own. And this thing came up instantaneously because what it did is it didn't really look at it. It just went out and read the metadata stored with the file when it's indexed, which is useful on its own account. So I should point that out, because what you've got going on here is, you know, as we talked about before, looking at your data is a real problem when you have big data sets. And you just can't graph this stuff. But here, even when you get like mins and maxes from, here you have there should be a variable called airtime somewhere here. Yeah, here it is, airtime. So, like what's with the negative airtime? So I leave the data this way most of the time when I do demos because it's valuable. You got an idea of how messy or dirty or strange your data set would be, and you didn't even do any work. Now, so we looked at that, and now I have a compute context. So this is the command for seeing what the compute context is, and the default is local sequential. So I have a 4-core. This is not going to really make a difference on my machine, but I have this, 2 processors with 4 virtual cores altogether. So I'm going to reset the thing to be parallel, and then check here and make it parallel. So now it's local parallel, and start the task. So we've got a task manager going on here. So you see where I am with memory usage. And so let's do something this is a command, Rx summary. We're just going to look at the data, the variable called arrival time. So I'm going to run that. And you see it chunking. So it ran through a whole bunch of chunks. It didn't take long, and it gave you the summary. Notice there's no quantiles in there because you don't want to compute quantiles unless you want them, and we have another function to do that. I won't do that now. What I'll do is try to have a look at things. And so we have, oops. We have some basic, I'll run this one. So here's a histogram. We want to look at the data. So the first histogram is again, just to make a point. So it's going to chunk through the data. And so it hit the wall on the one processor that's distributing the job, and now it's going to kick in. You'll see some more activity. So it's chunking through the data, and it's building a histogram. And what you're seeing here is it's telling you the total number of rows processed. And what you can do, I didn't really make any attempt to optimize this, but you can set chunk sizes for particular things. So what you don't want to do is get outside of your memory. So here it is, build a histogram that's not very illuminating and just what I want to show is. So let's get rid of that one and let's do a better histogram where I can take into account, I want to set some limits. So I can see from the previous one that most of it was blank. So let's build a histogram. What we're doing is setting, we're setting limits on where we're going to look at this variable. So I'm going to look at things that are above minus 60 in terms of arrival delays. So, maybe the thing got there an hour early. And then and somebody recorded it that way, but less than 250. So what I'm showing in here actually is that this command has a row selection algorithm, which is a very convenient kind of thing. You wanted a function that looks in big data, so it works with big data. And a number of the functions that we'll be using do that. And because you might want to skip things while you're processing on the fly. So I think the activity you're seeing here is that the parallel thing is, so this is the one core and that's the second core. So we're getting things distributed to the two cores. And here you have a nice histogram that's a little more meaningful. Looks to me like it might be a gamma, or, well, actually probably a beta. It probably ends somewhere here, so it's probably some sort of scale beta distribution. But, this is looking at a fairly large data set, and you didn't have to wait that long. And now let's run a regression model. And let me kick it off, and then I'll tell you some things about this code. So what I'm doing is I'm timing it, so that's the system. All right, 8 seconds. So it did that regression in 8 seconds, and it's a regression of arrival delay on the interactions of days of the week and departure time. And what I did was departure time was a numeric, so I made it a factor on the fly. So that's a beautiful kind of algorithm. It does a lot of things at one time. And it only took a few seconds to run. Here's a normal, this open source R summary function. So you see that this RxLin mod, which was the linear regression function, built a model called arrival delay. And now we're just going to interrogate that with normal summary function. You see, it's a pretty big function because we're looking at the interaction of arrival delay and departure times. And departure times are like on this 24-hour clock because I made a factor out of them. So it's returning a lot of stuff. And those of you who are R people, you know that you can just go in and get any of the coefficients or whatever and work with it. So that's pretty typical. And just to finish things out, because let's do a plot. So that's what we did. If you're doing, you know, we all had all factors there. So when the regression coefficients are just the same as the averages. And so what we just did was this little analysis of on that 123 million row data set. We've got departure hour down here, and we've got day of the week, so that you can see that it's not real good on the weekends. On Sunday nights, arrival delays, at least for that epic were, yeah.
So what do you think of the meaning of running a linear model for such a huge data set? Like when you look at the p-value of every single variables, it just turned out to be small and everything is strongly correlated.
Could you repeat the question, please?
Well, no, the first thing you said is right, correct. Yes, the p-values are worthless. And I am for just eliminating them, but people take some comfort in them because the p-value is just showing that it's different from 0. So that's another thing that, you know, we could talk about statisticians in the room here. When you're working with small data sets and you have this concept of statistically significant and practically significant, you know, what you want to work is in the realm of when they make sense. Now, it doesn't make sense to use p-values on very large data sets because all you're showing is that there's a difference between, you know, the value that you're computing and 0. And you're guaranteed that there's going to be a difference. I mean, you're on a finite arithmetic machine. After all, what you have underneath here is a computer that's trying to approximate the real number line. So there are lots of different reasons why they're going to be different. But the first question, doing a regression on a large data set, is sometimes meaningful. Because what you're doing is seeing if there are linear relationships. So it's one thing to build the model and look for relationships, and you may find them. And if you find them, it may make your life easier because you can make inferences. It's another thing to say, you know, to try to use the ideas of statistical significance and p-values the same way you do in small data sets. So separate those two things. Anyway, here's a graph. And at least for that epic, don't travel on, you're traveling on the weekends, expect delays. And I guess Thursday nights look pretty good. Now, if the gods of demos cooperate, what I want to show you here is running a similar regression, not the same one, because on a Hadoop cluster live. So there's this cluster out in the cloud somewhere that we're using for alpha testing. And I don't really have much control over this. They let me use it, kind of thing, if I promise not to break it. And they have a data set up there that's similar to the one that I just showed you, but not exactly the same. In fact, it's a bunch of CSV files. So it's not a XDF file. It could be, and it's not exactly the same file. So I'm going to run a regression that's very similar, but not exactly the same one, because I couldn't control what information's out there. But let me walk you through the steps here. So what we're going to do here is this big RHadoop. This is the function that's going to set up the Hadoop cluster. So these are the commands that are necessary to talk with whatever it is that Hadoop needs to know, whatever the job tracker, the scheduling system. So I got my username and my host name and all that secret, don't memorize that. And I've got some permission switches, and I've got, share directory. So things that you might expect have to get set. So I'm going to run those things, set them up, and then I'm going to run my cluster and set the cluster, and then see if we interrogate it. Up, so right back it came. So this is the result of setting the Hadoop cluster and interrogating it. So this is the kind of stuff that the IT people and the people who work with setting up Hadoop might recognize, the kind of stuff that's important for being on a cluster. And let's so I set that up, and now I'm going to create some variables here that just point to where my data are. And now this, because it wasn't the same file, so I got to do some, these commands are just to pre-process the data. So I'm picking out some variable names and setting some new levels in the factor. And let's get this running. We can talk about it later. And what we'll do is set the regression going. So let's see, we want this going. And well, all I did here so far is I've set the, what I'm doing with this command is setting up a, I have to declare a data object that the RevoScaleR functions will recognize. And you see there I have this Rx text data command, so I'm telling it what it is, and I'm using all that. So this becomes the label for my file. And just let me make sure I run that. Oh, that's I think that one's not going to work, but let it compute complete. So what I'm trying to do is to interrogate the, at least it shows you I'm on the Hadoop cluster, and I'm trying to get, interrogate the metadata. But I should have taken that out. There is no metadata for this because it was not in an XDF format. So that's a programming error. And that's not the kind of thing that you do when you're going to be in a demo. So let me try to kill that. Well, I'm just going to hit the panic button. I'm going to end that task. I'm going to have to restart my application, and then I'm going to pick it up from where and run my regression on the Hadoop cluster. So let's go to there. And once again, I have to set this up again. I don't want to do that. See where we are. So we're cool. And now let's do this regression model. And we're running that model now on the Hadoop cluster. And you can see there's not much going on. It's going to take a while for it to go, but we'll let it just go and talk about things. So now's a good time to take questions or. Yes.
That's from the back.
Yeah, it's doing Hadoop stuff.
Yeah. One of my questions, I understand that the idea with our revolution is that our revolution would exist to keep everything in the R IDE. How does working with Hadoop inside of R compare to, say, using R scripts with Hadoop streaming?
Well, I really don't know yet. I mean, this is new, but here's what I think is going to happen. I think for some people who are more in a, so if you're a statistician, or you want to be a statistician for the day, meaning that you want to get some inference problem done, and you can run a regression model, or a series of models like that, like logistic regression. So for instance, we have a, logistic regression is a classifier. We have a, we have a tree classifier, and we'll have a random forest classifier. You might want to do just that right out of the box, where you don't want to, where you have algorithms that have been professionally encoded and they're rock solid and they're going to run right out of the box, and you can work now in that limited framework of the algorithms that we have, beautiful ones, but yeah, limited. We don't have every algorithm in the world. Then you can work without breaking that flow. So we're trying to emulate that in-memory way of doing statistics that I talked about. Now, if you want to do something that's outside of that, and you've got to write your own algorithm, and we don't have it, then you have to do something like running R code and streaming, or running RHadoop with running R code and MapReduce jobs. So there's like always going to I think, be the right tool for the job at hand. And what we're trying to do is build tools that are rock solid and hit the sweet spot of somebody who's doing a certain aspect of statistical analysis. So the computation is completed. Yeah, it's not back yet. It says it's done, but I don't have control yet. Anyway, and then that'll come back in a minute. Oh, there it is. So, took 8 seconds to run a comparable job. There were 176 seconds involved in that. So what does that tell you? It tells you for something small like the airline's data set, you wouldn't use Hadoop. You do it on your laptop. And if you had RevoScaleR, you could do it in 8 seconds on your laptop. But what about, this is only a demo. People are going to have billions of rows and terabytes of data. If you wanted to build a linear model with that much data, then all the overhead that you incur with Hadoop and everything might be worth it. So that's all I basically wanted to say. And how are we doing on time?
We're fine. Give a few more minutes.
Okay, so I have time for questions. Let me see if there's something else that might be interesting to show you.
Does Revolution provide native interfaces with Hive and HDFS?
Yes, well, not Revolution, the open source package RHadoop. So it's HBase. There's HBase, there's a package in that open source project to do the database stuff, and then there's RMR, which I mentioned for the MapReduce job, and then there's a function for communicating directly with the HDFS file system for taking stuff in and out.
I have a question that might seem dumb, but been asked earlier about p-values and where you make a linear model and everything seems significant. So how do you interpret a model when it shows that everything is very significant? Which variables do you choose if you're going create a predictive model from that?
So, you don't use p-values. I mean, you don't do that. If you're going to, what you basically do in that area is move towards the way people do things in data mining. And you have a holdout sample. You do cross-validation. So my proclivity here is to do what statisticians have always done, sample. So build, there's nothing beats sampling. The world runs on sampling. Take random samples. Take very large random samples if you have to. But lots of random samples. Build your models. Use the sophisticated tools that statisticians have, like lasso and there's some great variable selection techniques that Hastie and that crew out of Stanford have just been going wild building the theory behind that. That's what you do. You do that, and you scale it up on a bigger model and see whether it still holds. And if it still holds on there, then go for it. Yes?
I don't really know the context of what you grew up about, more data with simple models does better than a sophisticated model and less data. But this is kind of that question, which is, at least to me, there's a difference between thinking like a statistician and thinking, I need to sample this data and then I'm trying to test a hypothesis of whether it generalizes to a population, right? That's one way to get more data, is just to say, I have the population, right? But the other context I could take that in is, of course, more data could build a better model if it's a different kind of data. Does that make sense? So thinking like a statistician, we don't always have, like those guys who did the Netflix algorithm, right? If you just use Netflix data, really sophisticated models, you do as well as the guy who brought in IMDb. He got more data, but of a different, not just more rows, right?
Exactly.
I don't know I think that it should
Okay, so let me try to sort it out this way. So lots of data is not necessarily big data. So imagine you got a single variable, and just to make it really simple, and you have 100 million rows of data, this single observations, this single value, and you plot it, and it makes a perfect normal curve. Now, if you think, and it makes a really good normal curve, and you do it in a simple standard deviation is small, are you going to process all that data every time? No, that would be silly. You use the theory of the normal distribution, and you say, yeah, I'm modeling this guy as a normal distribution with this mean the standard deviation, and I'm never going to process another data point if I think I'm only going to get the mode. Now, if you're in a different kind of game, and you're saying, yeah, most of it's normal, but I want to look for something that's 7 sigmas out, well, then you have to collect a lot of data to get 7 sigmas, but it depends on the question. But just more data is not big data. And the question you brought up there about the Netflix guys using different data sets, yes, that's an example of big data. That's an example where the large data set and very simple calculations did very well, because most of what you do in those kind of environments are sums. You do a lot of adding and multiplying. Basically, you're not doing sophisticated inference things. But I think there's a crossover point. There comes a and that's where it's interesting to try to run like generalized linear models on very large samples, and how do you do that with the underlying technology? So the other point is, you mentioned the word population. The brain dead interpretation of that model was, always use all the data. So people want to mistake all the data they have in hand with all the data of interest. Just because you have a lot of data doesn't mean it's the population. Right? You might just have a very big sample, and if you think of it that way, you have a very big sample, and you can get a meaningful result using a smaller sample, then why are you spinning your wheels? All right, that's it, I guess. Thank you.
Thank you. Joseph just flew in from San Jose, so we're really honored to have him here. That was wonderful. Thank you very much.